Bienvenue aux deuxième session pour les conférences des lauréats de l'ACP. Welcome everybody for the second session of the medal talks by the medal winners of the CAP. So we have Ebrahim Karimi, who won the CAP Herzberg medal. Ebrahim was born in Saqqez, Kurdistan, Iran. He received his bachelor's BSc degree in physics with an emphasis on mathematics from the University of Kerman in 2001, and his master's of science from IASBS in 2003, and finally his PhD from the University of Naples, Federico II, in 2009. He holds a Canada Research Chair in Structured Light at the University of Ottawa. His research focuses on structured quantum waves and their application in quantum communication, quantum simulation, quantum sensing, and material science. He has over 140 scientific articles published in peer-reviewed journals such as Science, Nature, Nature Physics, Nature Materials, etc., etc. His Rev letters. He is the co-inventor of 3 patents, a member of the Royal Society of Canada, College of New Scholars, Global Young Academy, Fellow of the Optical Society of America, and visiting fellow at the Planck Institute, Max Planck Institute for Science of Light, Fellow of the National Research Council, University of Ottawa Joint Center for Extreme Photonics, and finally an adjunct professor at IASBS in Iran. Okay. He received his Ontario Ministry of Research Innovation Science Early Researcher Award in 2018 and the University of Ottawa Early Career Researcher in 2019. He is also an associate editor of Optics Express, associate editor of the New Journal of Physics, applications of structured quantum waves, which is what he's going to talk on in modern science and technology, are the main subject of his research team. So please, Ebrahim, take it away, structured quantum waves.
So thank you very much, Professor Manu, for your kind introduction. And I'm really honored to receive these award by Canadian Association of Physicists. So it's really, it means a lot to me and to my colleague as well. So since we have limited time, I will start with the presentation. So we promised that we will finish in 25 minutes. So let me start with the presentation. And as I said, as you kindly said, so I'm at the University of Ottawa, and of course I'm also collaborating with several different institutes, including the recently launched Joint Center for Extreme Photonics. That is the center between National Research Council and the University of Ottawa, and at Max Planck Institute for the Science of Light in Erlangen. So if I remember, the last speaker talked about the way that you can just close your index finger, thumb finger, and see if you look at the bright light, you will see diffractions. I remember that was one of the reasons that I got motivated to do research activity in the field of photonics. So when I was in primary school, I always played with things, and I remember once I closed my thumb and index finger, and what I see some bright and dark regions, which I thought that my eyes has a special power, but later on I realized that also other classmates they had seen the same things. So I'm interested in light. Why? Because we can see easily. So when we talk about light, I'm sorry I go very technical. When we talk about light, we talk about electric and magnetic field, and in the quantum regime, these electric and magnetic field, they can be quantized, and you can assign a wave function to the photon, which you can control either the number of photon, or you can control the frequency, you can control polarization of the photon, or also you can control the spatial mode of them. So each of those different degrees of freedom, they will provide you some Hilbert space. They will provide you some mathematical space, which you can use them to doing some computations, to understand physics of light better. So we call these field structured light or structured photon at the quantum regime. So an example is shown in the right side, that when you go with the coherent superposition of different polarization, different spatial mode, and then you sum them coherently, what you end up with a structure which gives you the probability that you find a photon in each of those places with a certain probability distribution. And each place has a certain polarization and phase pattern. So I call this example, I would call it pizza-like structured light. So there are different techniques that you can create structured light. One of the techniques that we use in our laboratory, and my group, they use liquid crystal. So what they do, they take a piece of glass, they coat it with a polyimide, they orient the orientation of the polyimide on the surface of these, and then when they insert liquid crystal between two pieces of glass, which they have a specific orientation and structure, then liquid crystal will pick up structure, and based on Pancharatman Berry phase, then you can shape optical beams. So you can get a slab of glass, which is made of liquid crystal, and you can almost create any polarization and intensity distribution, intensity and phase distribution for the light. So for example, you can create a different type of beams like inch-Gaussian beam, or you can create airy beams, or you can create very, very rich topological structures. For example, this is a case when you can create orbital angular momentum light that carries orbital angular momentum of 400. And this is not the record. The record is about, I think, 10,000. So with this technique, you can also shape the beam, as I said, in a very strange or very controlled way, and you can shape the optical beams. So, for example, one of the interesting example is a magic plate, which was invented by Chinese almost 2 millennia ago, 3 millennia ago, and when they cast a mirror. When you look at the inside, look at the mirror, you don't see any pattern. While when you shine the light on the mirror, if you look at the reflection of this at the far field, what you see, you will see a hidden image there. This was resolved by Michael Berry in 2017, and what he found that indeed the Chinese, they implemented Laplace transform of the image that they want to create it. So in my laboratory, people also, they were able to create these, and what they got a pattern which essentially doesn't have a focus. It has a depth of focus, which is a certain, you can have an image in a certain volume. And of course, being at the University of Ottawa and collaborating with Paul Corkum and Bob Boyd gives you the opportunity to transmit and shape the optical beam, not at the visible range, but also at the XUV range. So when you go to really, really short wavelength, and at the short wavelength, it's extremely difficult to find optics. However, what you can do, you can use the conservation laws that you have due to the interaction with the material and impinging specific structure to the high harmonic at very, very short wavelength. For example, we were able to create orbital momentum at 17 harmonics, or 15 harmonics, or 13 harmonics. And very recently, what we have done, by controlling the relative phase between second harmonic and the fundamental beams, we were able to create a current by interacting with a semiconductor. And this current will induce a magnetic field, which is an order of few Tesla. So structuring of optical beams at different domains will give you different feature. However, we have to also go deeply in mathematics. When we talk about optical beams, then you have polarization, as I said, phase, and spatial mode. So what you can do, you can control all of these different degrees of freedom, and also you can understand the physics behind of each. So for example, if you look at the polarization may have different singularities in defining the Stokes parameter, defining the way that the vector of the electric field is oscillating in time and space. For example, usually in the case of circular polarization, it probes on a circle, while in the case of linear polarization, it goes on a linear line. So essentially, for the first case, when we assign an ellipse to the polarization of the light, for the case of circular polarization, this ellipse doesn't have a major and a minor axis. So we have a singularity in defining the orientation of the ellipse. And in the case of linear polarization, what we have as a problem, we don't know which direction of the electric field and which direction the electric field is oscillating. So we assign singularities to the polarization of the light. We can shape the singularities in such a way that they form a three-dimensional topology, although the light will, Maxwell equation will dictate that the electric field and magnetic field, they should be transverse, but under tight focusing regime, you can create a three-dimensional topologies. For example, in the case of Mobius, or in the free space, you can create knots, or even you can assign a frame to the knot, and you can get a frame knot, like something like what I have with my tie knots. And we used this knot topology will give you a very practical tools. You can use it as a backdoor for the communications. For example, you can assign prime numbers to each braids, which has a specific twist, and then you can use it as a backdoor to send encrypted messages. So this is a very recent work of our group. And also in the quantum regime, we are very interested to understand how we can create correlated photons, which all of those different degrees of freedom, they are coupled to each other, or they are correlated beyond the classical correlation. So for example, in one of the recent work that we have done, we look at the way that you can create spontaneous parametric down conversion photons, which can give you a specific correlation in the spatial mode of spatial mode degrees of freedom. So since we are moving to the quantum regime, this structured light will provide you more alphabets. So we can go beyond 0 and 1 bit. And then what we can do, we can send more information per pulse. For example, in the case that you see here, we can choose 7 alphabets. And instead of 0 and 1, we can work with 0 and 6. And then we can send more information. But also in the quantum regime, what we can do, we can also increase the level of the noise in such a way that the communication is secure. So for example, in the case of 4-dimensional encryption, you are not only sending 2 bits of information at the 0 error, but also you can establish a secret key when even you have about 0.18 error, or 18% of the error, which is forbidden by the case of the 2-dimensional space. So during past years, my group extensively worked in the quantum encryption and QKD, especially in the free space between 2 buildings at the University of Ottawa, underwater channel, which I briefly discussed about that, also in the fiber channel. So we established, people from my group, they established a free space link between University of Ottawa and National Research Council of Canada in Montreal Road, which is about 5.4 kilometer free space link. And they started to build up decks. They started to isolate the optical table from the deck. And even the link is now available on the Google Earth, and you can just use Google Earth or Google Map, and you can find the 2 links there. And they put optics there, and they started to do encryption in the spatial mode. And the other side, they had a receiver. They could receive the signal, and they could decode it. And this is the sender, which is in the I think is M50, which is a library at Montreal Road, a library of NRC in Montreal Road. And on the other side, when we go to the receiver, is installed on the roof of Colonel By in the campus of University of Ottawa. So sender you can encode in any degrees of freedom that you want, and on the receiver side you can receive it. So you can see in the lower corner that the sender is located there, and on the front you will see the arc building. So we recently got a scintillometer, which we can monitor the turbulence, which is an important factor for the quantum encryption in the free space link, and also an adaptive optic system with a supercomputer, which allows you to do a fast compensation for the turbulence. And also during last 3 years, my group also, they start to do quantum, they start to send information through underwater channel, first at the swimming pool of one of my student parents' house, and then they went to a cottage in the Ottawa River, and they tried to send information through the Ottawa River. And last year they did through underwater channel in one of the NRC flume in Montreal Road, and they were able to go up to 30 meters without having compensation for the turbulence and without even beam tracking system. So when you go with underwater QKD, you have to go with the different wavelength, which is very different from the free space one, because almost water is almost opaque at many different wavelengths, apart from green and blue. And this is one of the examples that Alicia tried to send blue and green light together, and you will see that the absorption due to the absorption of water at the green is much higher than blue. And then also they tried to do encryption in the vector modes, and still they were able to reach to 30 meters and at the data rate of 80 kilobits per second, which is extremely good for underwater communication. And a nice story, when I received a call from Shoini regarding the award, first I thought that she's calling me regarding to this manuscript, because a couple of days before the call and receiving the message from Shoini, we posted this article on arXiv, which we show to the people that during communication between satellites in the curved space-time geometry, also you have to be extremely careful with encryption and decryption technique. Why? Because the wave function of the photon or any particle that you want to use for communication will be perturbed. For example, if you just send a signal in the longitudinal mode, then after propagation you will have some digression, and then you will have higher modes to be excited. So we believe that this is extremely important for any space communication. However, structuring beams is not limited only to light only. So you can go with almost any particle. So for example, if you go with massive particles, we know very well that we deal with wave function. These wave function can be solved in the relativistic regime, can be resolved in non-relativistic regime without interacting with the potential. It can be a free particle. And when you deal with this, it is interesting that the free particle also can be quantized along the general mode and also along the transverse degrees of freedom. So associated to each of those cases, you can have certain quanta, which you can use them to manipulate this spatial mode or transverse mode and use them for quantum information or using for material science application. So it is interesting that you can create some certain modes, which we call them twisted particle, twisted massive particle. And in that specific case, if the particle is electron, it carries a magnetic moment along propagation direction. This is in addition to the spin degrees of freedom. Spin is intrinsic property, and it can have only 2 quanta for the electron. But in this case, by only shaping the wave function of electron, which is in free space, so electron is propagating without interacting with any sample, any potential, but just twisting it, you can get an additional degrees of freedom, and that gives you a magnetic moment along propagation direction, which is quanta, is unbounded. So we started to work on these. Of course, this was predicted by one of my good colleague, Konstantin Belyuk, in 2007. And then after that, many different groups, including our group, we worked on this. So in 2014, we were able to create the first phase hologram for electrons in such a way that when electron beam is passing through this phase hologram, it picks up the phase, and you will see the diffraction. And then you will see that at first order of diffraction, you will see a single electron which carries orbital angular momentum. And this single electron has a magnetic moment which is quantized along propagation direction. So this has application to probe magnetic field. And for example, in the example on the left side, we show that by interacting not physical interaction, of course, feeling the magnetic flux, you can detect the amount of the magnetic field that electron beam will see it during the propagation. Or even we answer to some of those fundamental questions like filtering the spin of free electrons. So for those people, they work in electron microscopy, they know very well that filtering the spin of free electron is a big challenge, and is almost impossible to get a free electron in the middle energy level that has a certain spin quanta. So what we have done, we couple spin to orbital angular momentum degrees of freedom in the free space, and then we say that we can sort the orbital momentum, and this coupling between spin and orbit will allow us to pick up a certain spin state. So here I want to just show you that how the holograms and the techniques that we use for encoding for shaping electron beam is very complicated. So this is a size which is below the size of my hair, is below 80 micron. And then you have to go with tens of nanometer scale writing techniques in order to manufacture one of those holograms that can be used to shape electrons. There were other techniques. So we developed also a dynamic way that you can control twisted electron, which is based on the dynamic phase by only applying a few volts between two plates. And then when electron is passing by, it sees the potential, and based on the space varying potential that you see, you can imprint a phase quanta to the electron. And in a gang collaboration with one of my colleagues in Switzerland, in Fabrizio Carbone, what we have done also, we look at the interaction of the electron with the surface, near field surface plasmons. And this way also we were able to create a twisted electron in a really fast fashion. So why we care about that? Because electron microscopy can be used to detect objects. And one of the objects, for example, that right now also people they are extremely interested in is detecting, for example, protein viruses. And some of them, they have a certain symmetry. And for example, this is one of the protein that our group, they were interested in. And this has a 7-fold symmetry, if I recall well. And just looking the way that you can find the sparsity of the image and sorting them gives us a huge boost in detecting those proteins in a sample. So we have a European project led by my colleague Vincenzo Grillo in Italy, which the aim is building up an electron microscope which can, when you know the physical symmetry of a sample, you can use them. You can use and design a sorter which can sort, which can detect those proteins or those samples with the minimum number of interaction. With this, I will conclude my talk. And in a summary, I would say that we are interested to answer to fundamental questions. Also, we are interested to build a quantum microscope, which unfortunately Canada is not interested. European Commission is more interested in this direction. And also with my colleagues in Calgary and in Waterloo, UBC, all from coast to coast to coast, we are interested to build up quantum internet in Canada, and we are contributing to this field. And of course, this is not a single person work. Is many people work. So including many of my great students. So if I go by names, Hugo Larocque, which he worked on shaping light beam by using liquid crystal technology and designing the three-dimensional topologies like knots and frame knots. Alicia Seat, which she at that time was a bachelor student, led the free space QKD project with Frederick Bochard and Robert Fickler. Felix Hufnagel, Alicia, Fred, Ingwen, which they work, and Florence, which they work extensively in underwater quantum communication. Alessio, Manuel on the 3D topology, and also on the interaction of structural light in SPDC, and how the correlated photon will be generated. Kassem Exifad, who worked on propagation of light in the curved space, and many other students which they extensively worked, and they helped me during the past years. And obviously my collaborators from Bob Boyd, Paul Corcom, Gerd Loix, Miles Paget, Yakira Harnov, Chabat Heshami, which helped a lot with the free space QKD, Duncan England, Ben Sussman, and many others. And at the end, of course, this was impossible without the contribution, without the help from our supporters, which University of Ottawa, mainly Canada Research Chair Program, Canada Foundation for Innovation, NRC, CFREF, and NSERC, and Max Planck Institute. So thank you very much.